everyone, in this video I'm going to talk about what is an integral domain. And the short answer to this question is it's a special type of ring. So if we think about what we've done so far in abstract algebra, we've first started our study of abstract algebra with groups. And, a group is kind of a general thing. It's, you could think of it like a shoe. And then we got more specific and we said, okay, of all the type of groups out there, there are some very special ones that are called rings, right? A ring is an additive abelian group, and then it's got extra structure on it with respect to multiplication. So we had this idea of rings. And so the idea here is you might have the set of shoes out there, but there are some specific type of shoes like sneakers. And then within the category of rings, there are some additional restrictions. We can say we only want to talk about certain types of rings or rings with very specific criteria. And that brings us to this idea of integral domain. So I'll just put a little subset in here and I'll call it an ID for integral domain. And that's like saying, hey, I've got sneakers and I'm going to talk about a certain type of sneakers, like maybe just the leather sneakers. For some reason, I want to talk about leather sneakers. So it's just that I'm getting more specific about what I'm talking about. And, just like a leather sneaker might be really good for some very specific things you're going to do, that's the same with integral domains. They're really nice to work with. So before we define what is an integral domain, we need to understand what are zero divisors. So we'll start off with a ring, we'll call it R, and we say that A, an element of R, where A is non-zero, A is a zero divisor if and only if there is some B from the ring R, such that A times B equals 0 or B times A equals 0. And it might be the case that both of these are true. So it's not an exclusive or. So we'll take a look at how this could possibly happen, because it certainly seems a little bit weird. In the real number system, the only way we get a 0 is if one of the factors was a 0. But that's not always the case. So zero divisors are a little bit sneaky, and you definitely want to avoid them if you can, which is why we are defining them here and how to avoid them. The next term we need to define is something called a unit. So again, we're in a ring R, and here we need to make sure we're in a ring R with an identity. So we say if R is a ring with a 1, then U from R is a unit if and only if there exists some other element, I'll call it V from R, such that UV equals VU equals 1. So this is basically saying that the units in R, they're the set of elements that have multiplicative inverses. So the notation for the set of units looks like R with a little multiplication symbol. So this is the set of units in R. So it's a set of elements that have multiplicative inverses. So what I'd like to do is define what we mean by an integral domain and then go through and look at a few examples. So the integral domain, the definition of an integral domain is a ring R with identity not equal to 0. And it's a ring that has no zero divisors. So it's a lovely place to be. Again, zero divisors are a little bit sneaky and strange and weird. And if you don't have to worry about them, life is much better. So let's take a look at a few examples, and we will ask ourselves, is it an integral domain or not? So examples, and the first one I'm going to look at is the ring of real numbers. So we've talked about this. This is a ring. In fact, it's a commutative ring. We've shown that in another video. And it does have an identity. It has a 1 that's not equal to 0. So far, so good. And we know there are no zero divisors. The only way you get A times B equals 0 is when one of them is 0. So there are no zero divisors. Nothing sneaky going on here. And so this is an integral domain. For our second example, let's think about the ring of matrices, the ring of 2 by 2 matrices with coefficients coming from, or entries coming from the set of real numbers. This is not a commutative ring. It does have a identity. So I'm just going to say this is a ring with quote unquote a 1. And remember that identity was our identity matrix, 1's down the diagonal, 0 everywhere else. And so really the question here is it an integral domain? Are there any 0 divisors? So if we explore this for a moment, there are 0 divisors here. So let's say note 1, 0, 0, 0. That's not 0. And I can take another element from my ring of 2 by 2 matrices with entries from R, 0, 0, 0, 1. If I multiply these together, first row, first column, that's going to be 0. And I keep on performing my matrix multiplication here, I end up with the zeros. So we had 2 elements, A and B, giving us 0, where A is not 0, B is not 0, and so this means there are 0 divisors. So this ring has 0 divisors. You know, it's this totally weird situation. You have 2 things, they're not 0, but you multiply them together and you get 0. You get the 0 matrix. So this is a little bit of a nasty ring to work in. We do it all the time. It's fine, but we have to be careful here. So we can't divide matrices, for example, in this ring. Anyways, the conclusion here is this is not an integral domain. Okay, and for my third example, I'll just make a little bit of space here up at the top. I'll leave my definition on the board, though, for us, so we can refer to that. The third example, so let's say example 3. Example 3, I'm going to look at the ring 3z. So this is the ring of integer multiples of 3, and we've explored this in a previous video. So we said there's things in here like -6, -3, 0, 3, ... And it goes on forever in both directions. We've got integer multiples of 3. And this is a ring. In fact, it's a commutative ring, so that's nice. There is no identity element. There is no 1. Right? In fact, physically, there's no integer value of 1. There is no multiplicative identity. So right away, I am out of luck. This is not an integral domain because I needed to have a 1. So this is not an integral domain.